We're going to take a look at something called the divergence test, which is going to help us analyze the behavior of a series that isn't geometric and isn't telescoping, and for which we might have some difficulty coming up with a closed formula for its partial sums. The first part of the divergence test tells us that if we have a convergent series, then the limit as n goes to infinity of the corresponding sequence must be 0. Let's take a minute to look at why this might be the case. If we have a series that we know converges, then we also know that the limit as n goes to infinity of its partial sums, s sub n, must exist. Let's call that s. If that's the case, then it's also true that the limit as n goes to infinity of the sequence of partial sums s sub n minus 1 must also be s. We know also that the nth partial sum s sub n is the same thing as the n minus first partial sum plus the term a sub n. If we take the limit of both sides on this equation here, we get that the limit as n approaches infinity of s sub n equals the limit as n approaches infinity of s sub n minus 1 plus a sub n. We can use some properties of limits. In particular, we can use the fact that the sum of the limits is the same thing as the limit of the sums to say then that the limit as n approaches infinity of s sub n is equal to the limit as n approaches infinity of s sub n minus 1 plus the limit as n approaches infinity of a sub n. We can replace each of the two limits of partial sums with their value s that we established earlier. In other words, we now get that s is equal to s plus the limit as n goes to infinity of a sub n. If we then subtract s from both sides, we see that 0 must be the limit as n goes to infinity of a sub n. Now, if you're currently thinking to yourself, how is it helpful to show that a series is convergent if I already have to know it's convergent to use this test? If that's what you're thinking, give yourself 10 points and then hang on a second. Whenever a logical statement is true, it turns out that it's contrapositive, the statement we get by reversing the direction and negating both parts, is also true. What that tells us, in this case then, is that if the limit as n goes to infinity of a sub n is not 0, then we can conclude that our series diverges. It's very important to recognize that when using this test, the only thing it can tell you for sure is that a series diverges. You are not able to use this test and conclude for certain that a given series converges. In order to use the test, first you'll evaluate the limit as n goes to infinity of a sub n. If that limit is not 0, then you are certain that the series diverges. However, if the limit is 0, the test is inconclusive, and you'll need to use another test to find out whether or not the series converges and what its value is. In order to explore how this test works, let's examine the series, the sum from n equals 1 to infinity of n over n plus 1. The divergence test tells us we can inspect the limit as n approaches infinity of the corresponding sequence n over n plus 1. Elementary limit techniques tell us if we multiply the top and bottom by 1 over n, we have the limit as n approaches infinity of 1 over 1 plus 1 over n, and that is clearly equal to 1. 1 is definitely not 0. So, since the limit of the corresponding sequence is not 0, we get to conclude that this series does not converge. For our next example, let's examine the sum from n equals 1 to infinity of e to the negative n. Applying the divergence test, we get to inspect the limit as n approaches infinity of e to the negative n, which is the limit as n approaches infinity of 1 over e to the positive n. And clearly, as n gets larger and larger, our denominator gets bigger and bigger, which means that this limit is 0. The fact that it's 0 tells us that the divergence test is inconclusive. Divergence, there we go, I spelled it right. The divergence test is inconclusive. We'll need another test to determine if this series diverges or converges. But if you look at it, you can see that the sum from n equals 1 to infinity of e to the negative n is a geometric series. We have 1 over e to the n power. Now remember, when we use a geometric series, that it needs to start at 0 in order to apply our formula. So we're going to rewrite this as the sum from 0 to infinity of 1 over e times 1 over e to the n. So this is geometric. We've got an a value of 1 over e and an r value of 1 over e. So this becomes, this series is equal to 1 over e over 1 minus 1 over e, which is 1 over e minus 1 over e, which when we take the reciprocal of the bottom and multiply, we get 1 over e minus 1. So we can see that the divergence test was inconclusive, but this series does in fact converge to the value 1 over e minus 1. Now, just in case that last example lulled you into the false belief that when the limit is 0, the series does in fact converge, we're going to look at this next example. Here we have the sum from n equals 1 to infinity of 1 over n, and we know that the divergence test tells us we should inspect the limit as n goes to infinity of 1 over n. Well, that limit is equal to 0. Now, that implies, or that suggests to us, that we need to look further in order to determine if this thing converges or diverges. The divergence test is once again inconclusive. In fact, we'll show in another video that by the integral test, this series does in fact diverge. To sum up everything we've learned, to use the divergence test, you're going to evaluate the limit as n goes to infinity of the corresponding sequence a sub n contained inside of your series. If that limit is not 0, then you know for certain that the series diverges. If the limit is 0, the test is inconclusive. The series may diverge, but it also could potentially converge, and further exploration is necessary.